So this is a review for an exam in a multivariable calculus class. We're dealing with an exam with double integrals and triple integrals as the primary topics. First question, we want to evaluate the double integral. We're going to go 0 to 1 in y, 3y to 3 in x, and we want to integrate e to the x squared. So at first glance, this looks like just a standard iterated integral question, but the first thing we'd want to do then is integrate e to the x squared with respect to x. Now, unfortunately, there's no nice antiderivative there. There's no substitution you can do, anything like that. So what you're going to want to do is switch the order of integration because you can integrate e to the x squared with respect to y. Just be y times e to the x squared. So I'm going to draw out my region here to switch the order of integration. So when I draw this, let's see, I'm getting y goes from 0 to 1. So this is sort of my y-axis. On the x-axis, x goes from 3y to 3. So we're going to have a 3 out here. And then x equals 3y is going to be a line that goes through the origin. And I also know if I look at this, it turns out that this point 3, 1, x is 3, y is 1, so x equals 3y. So that line is going to be this line right here. So this is really the line x equals 3y. And let's see, and so x started at the line x equals 3y and went up to the line x equals 3, which is right there. So our region is this sort of triangle here. So we're going to rewrite this integral. Do a double integral. Still going to integrate e to the x squared, but now we're going to do this dy dx. So x is going to range from 0 up to 3. So we get bounds 0 to 3. Y, I'm going to get a rectangle, sort of goes from y equals 0, that's the x-axis, up to this line x equals 3y. So y equals 0, x equals 3y, well you could solve that for y, and you get y equals x over 3. So then we have y in terms of x. So we get a new integral like this, and we're just sort of hoping this works out. It will. Let's try that. So I'm going to integrate, let's say I get 0 to 3 in x. When I integrate with respect to y, I get e to the x squared just times y. E to the x squared is a constant as far as y is concerned. And I evaluate that from y equals 0 up to y equals x over 3. Got dx left. So I get 0 to 3. When I plug in y equals x over 3, I'm going to get, write it in front though, x over 3 e to the x squared. When I plug in 0, I get 0, so I would subtract a 0, but that doesn't really show up. So what I get is an integral 0 to 3, x over 3 e to the x squared dx. And now I have this x out here when I integrate with respect to x, and I can actually use that to let u equal, to let u equal x, not 2, u equal x squared. And then du is 2x dx. And so this integral is, let's see, we're going to get, when I get e to the x squared, let's see, x dx is du over 2. So we have the 1/3, but we pick up a 1/2. So we get a 1/6. And we have sort of an integral e to the u, but that's just going to integrate to e to the u, which is e to the x squared. We go from 0 to 3. So we get 1/6. We do e to the 9th. We plug in x equals 3. We plug in x equals 0. We get a 1, so e to the 9th minus 1. So our value is 1/6 e to the 9th minus 1. Next question. Oops. Okay, we want to evaluate the double integral of x plus y times x minus 2y. It's an area integral where our region we're integrating over is a parallelogram with vertices 5, 2, 6, 1, 8, 2, and 7, 3. So let's sketch this out here. So let's go here, let's say somewhere out here. Let's just make this sort of actually fairly accurate here. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. All I need to go. So we've got 1, 2, 3, 4, 5, 2. So there's 5, 2. We have 6, 1 is going to be like right there. We have 8, 2, going to be somewhere like that. And then we have 7, 3 is going to be somewhere like that. So our parallelogram looks something like this as we go along here. So we're integrating over this region. Now you could just do a double integral here and do it like, say, dx dy. The issue there is once you fix y, you'll get sort of horizontal cross sections. and you'd need to split into sort of two pieces. So you'd have to split here. You'd find this equation of line, this equation of this line, equation of that line, equation of this line, equation of that line. Split that into two pieces as you go along. It would work out fine. It takes a little bit of work. What I'm going to do instead is change variables. So what I'm going to do here is, I'm going to try to erase this red here. Probably should have drawn that solid, my technology. But anyway, what we're going to get here is these points. Let's label these. So this was 7, 3. This point was 8, 2. This point was 6, 1. This point was 5, 2. And what we're going to get here, we want to find the equation of these lines. Now, the line from between 7, 3 and 8, 2, y goes down by 1, x increases by 1, slope is -1. And when I get that, the form is going to be x plus y equals some constant. Well, 7 plus 3 is 10, 8 plus 2 is 10. That's x plus y equals 10. If you don't kind of follow that x plus y from the slope is -1, what you could do is just do y equals mx plus b form or something with 2.7382. You could rewrite that equation as x plus y equals 10. It'll work out. Now, to be parallel on the opposite side, so that's that side there, the opposite side, we should get x plus y equals something else. Well, 5 plus 2 is 7, 6 plus 1 is 7. So this line here is x plus y equals 7. Okay, our other two sides, so here, let's see, change in y over change in x. We get 1, 2 minus 1 is 1, 8 minus 6 is 2. That's a slope of 1/2. So let's see, that means y changes by 1 for every 2 that x changes. So I should get something like x minus 2y should be a constant. So 6 minus 2, that's 4. 8 minus 2 times 2, that's 8 minus 4. That's also 4. So I get x minus 2y equals 4 on this sort of bottom right side. And then I get an x minus 2y equals something on the upper left. So 7 minus 2 times 3 is 7 minus 6. That's a 1. 5 minus 2 times 2, that's a 5 minus 4. That's a 1. So we have this all set up. A hint here, if you're not comfortable with these, is if you look at the integrand here, this is set up to be nice. Notice this x plus y here is one of the factors in our integrand. The x minus 2y is another one. Now that doesn't have to work out. It just sort of tends to be when people set these problems up to work out nicely that that's the case. Okay, so what we get here is our double integral over our region R. We're going to convert this to a uv integral. Now I'm going to let u, how about be x plus y, and v be the x minus 2y. So then I'm going to convert this to a uv integral. Then x plus y, that's u. X minus 2y is v. And if I look at these bounds, I can do this as du dv or dv du. It does not really make a whole lot of difference. V is the x minus 2y, so that goes from 1 to 4. So my v bounds go 1 to 4. My u bounds go from x plus y equals 7 up to x plus y equals 10. And all we're missing is our Jacobian here. So we have to sort of have a scaling factor when we change variables. And to calculate that, you could take u equals x plus y, v equals x minus 2y, solve for x and y in terms of u and v, do the Jacobian that way. So that would be sort of the standard approach. What's simpler is to do sort of the inverse or reciprocal of the Jacobian. So it's going to be take a Jacobian of uv with respect to xy. So it's going to be a partial u with respect to x, partial u with respect to y, and then a partial v with respect to x, partial v with respect to y. So I get this determinant, and actually it's going to be the absolute value of this that we plug in. So in our case, this determinant, let's see, u with respect to x is 1, u with respect to y is 1, v with respect to x is 1, v with respect to y is -2. So I'm going to get -2 minus 1. That gives me a -3. So the scaling factor we put in is always an absolute value of this, except this is not what we want. We want the reciprocal of this, because we did u, v, x, y. So what I'm going to end up putting in here is a 1/3, really, as our Jacobian. Now again, you could have solved u and v equations, get an x as some function of u and v, y as some function of u and v, done partial x with respect to u, partial y with respect to u, well, partial x with respect to u, partial x with respect to v, partial y with respect to u, partial y with respect to v, then everything kind of flipped over, and then you would have gotten negative 1/3 here. But it's sort of simpler to do things this way than to find the inverses. Okay, now we just need to calculate this double integral here. So this is a 1/3. Want to integrate with respect to u, I'm going to get v times u squared over 2. U goes from 7 to 10 dv. Let's say I'm going to pull the 2 out and get a 1/6. Integral 1 to 4. Let's see, v times 10 squared is 100, minus 7 squared is 49. So that's going to be a 51 over 6. And I'm going to integrate v and get a v squared over 2 from 1 to 4. So I'm going to end up with 51 over 6 times 2 is 12, times 16, 4 squared minus 1 squared is 1. So we get, let's see, 51 over 12, maybe we write it times 15. Now let's simplify what we can. 15 is 3 times 5. 12 is 3 times 4. Cancel the 3's. I have powers of 2 on the bottom. Top is odd, so that's it. So I'm going to end up with 255 over 4. Okay, on to the next question. So this one, we want to evaluate the integral, double integral. So we're going y from 0 to 1, x from 0 to square root 1 minus y squared of sine of x squared plus y squared. First thing to do, let's graph this region here. So what we're going to get is, let's see, y. Let's do a better job here. So here's x. Here's y. Y goes from 0 to 1. X starts at 0, so we're going to be in the first quadrant. X goes from 0 up to square root 1 minus y squared. So that's x is square root 1 minus y squared. If you squared both sides, you get x squared is 1 minus y squared. And then add y squared to both sides. You get x squared plus y squared equals 1. That is, we have a circle of radius 1. Whoops. So we get this circle of radius 1 there, and this is really our region that we're integrating over. Now, again, you could do this as an iterated integral. Problem is, I don't know how to find an antiderivative of sine of x squared plus y squared. Now, you might be able to do some kind of substitutions here, but the one that's going to make sense here, that's sort of screaming out to me, is to switch to polar. So the reasons I see that is x squared plus y squared. In polar, that's r squared. So that works out pretty nicely. And then this quarter circle is going to have really nice descriptions in terms of bounds for polar. So when we go to polar, let's just write this up. We get a double integral. We're going to get sine of r squared. Our Jacobian is r. And let's do this dr d theta. Note that Jacobian of r is going to be really useful because then integrating sine of r squared, you let u be r squared, du is to r, you have the r out there. In any case, let's do our bounds. Theta starts at theta equals 0, goes up to pi over 2. So we go 0 to pi over 2. R starts at 0 and goes out to this circle of radius 1. So our equation here is really r equals 1 for the circle. So r goes 0 to 1. So I get really nice bounds here. So this makes me feel like this is probably the way this was intended to be done here. And now we need to integrate, okay, with respect to r. I'm going to get 0 to pi over 2. Again, I let u be r squared. du is 2r dr. And what I'm going to get, let's see then, is r dr is du over 2. So I'm going to get a 1/2. I'm going to get a sine u. That's going to integrate to a negative cosine u. Well, negative cosine u, I don't need to really write u, and negative cosine of r squared. Here. And then we're going to go from r equals 0 to r equals 1, and then we have to do a d theta integral. Whoops. Okay. Now let's see, we can pull the 1/2 out in front. We get an integral from 0 to pi over 2. Plug in 1, we get negative cosine of 1. That's not a nice thing. Here it's just sort of some value. Negative cosine of 1. We plug in 0, we'll get minus a negative. That's plus cosine of 0. Cosine of 0 is 1. D theta. Here. And so then what we're going to get, let's see, we're going to get 1 minus cosine 1. So we end up with 1 minus cosine 1 over 2. And then there's no theta here, so when you integrate, you get a theta, and you go from 0 to pi over 2. That's basically just going to be multiplied by pi over 2. So you end up with is 1 minus cosine 1 times pi, and then you get the over 2, that'll be a 4. When you subtract the 0, that's a 0. So your answer should be 1 minus cosine 1 times pi, all over 4. Next question. Okay, so here we're going to do a triple integral for some domain D of x plus y, where D is the region between z equals 2 minus x squared and z equals x squared, and then we have y goes from 0 to 3. So this is a three-dimensional region, but if you look at the bounds, we have two equations that sort of relate z and x. This one sort of wraps around. But y is sort of independent. So what I'm going to do, well, y is independent of x and z. I'm going to draw in the xz plane. Here, these equations 2 minus x squared and x squared. So z equals x squared, it's a parabola. Z equals 2 minus x squared, also a parabola, but it starts at 2 and sort of curls down here. So in the zx plane, we're looking at this region here, and then y just goes from 0 to 3. So it's going to be a cylinder or a prism. It's a picture of what this looks like. So here's our sort of xz plane shape here drawn in Mathematica a little bit more nicely than my drawing here. So this matches this region in here. But then y goes to 0 to 3, it just sort of makes that into a cylinder here. So it just sort of scales back there, and you get sort of the same shape, that constant cross-section here. So there's sort of our shape. And so to integrate this, I'm just going to do this in rectangular. So I'm going to do a triple integral. Let's see, how about we do this, I probably in cross-sections, let's see, I probably want to do a vertical cross-section to go to sort of z goes from the bottom to the top. Here, if I do horizontal, I'm going to have to split at whatever this value is here. So what I'm going to get, let's see, we have x plus y. So I'm going to do dz first, how about then dx, then dy. So y goes from 0 to 3. X, well, goes from whatever this x coordinate point is, x coordinate that point is, to x coordinate this point. Well, that's where the two z functions are equal. So to figure those out, I have to do 2 minus x squared equals x squared. So I'm saying 2 minus x squared equal to x squared. You give me 2 equals 2x squared, 1 equals x squared. X is plus or minus 1, so I have a minus 1 and a plus 1. So x is going to go from minus 1 to plus 1, range here. And then z just goes from the bottom function, which is x squared, to the top function, which is 2 minus x squared. Now we just need to integrate this. So first integral, we're going to integrate x plus y with respect to z. Well, that's just x plus y times z. And z will go from x squared up to 2 minus x squared. I have a dx dy integral. So I have an integral 0 to 3, integral negative 1 to 1. We're going to get, let's move this up here, so I'll get x plus y times 2 minus x squared minus x plus y times x squared. Dx dy. Now I'm going to have to simplify this out and do a little bit of algebra here. So that's my choice. When I multiply these out, let's see, I'll get a 2x minus x cubed plus 2y minus x squared y. And here I'm going to get a minus x cubed minus x squared y. Dx dy. Looking at this now, I have x plus y as a common factor. I could have factored that out and done the 2 minus x squared minus x squared again, 2 minus 2x squared. Might have been a bit simpler. This will work though. So I get 0 to 3, negative 1 to 1. Let's collect like terms. Let's see, we have a 2x. We have minus 2x cubed. We have a plus 2y. And then we have a minus 2x squared y. Dx dy, and then we're going to integrate this. One thing that's not going to be a huge help, but will be useful, is that because my x bound is symmetric, negative 1 to 1, these odd powers, they're going to go to 0 once I plug things in. So when I integrate this, what's going to happen? I'm going to get, let's see, 2x will integrate to x squared. when you plug in a 1 and then subtract a -1, well, because that's an even exponent, that's going to be something minus itself. That's going to go to 0. This next one is going to be x to the 4th over 2, so 2 over 4. That's also going to go to 0. So these two you don't really need to worry about because of that. And then I'll get a 2yx minus 2x cubed y over 3. And then x goes from -1 to 1, dy. And we get an integral 0 to 3. Let's say when we plug in 1, we get 2y minus 2/3 y. And we plug in a -1, we're going to get minus -1, we get a plus 2y again. And we're going to minus 2/3 y again. So what you end up with is, let's see, 2y minus 2/3 y, that's 6/3, 4/3 times 2. Looks like we're going to integrate 8/3 y dy. So that's going to end up being here. Let's see, we've got 8/3 times y squared over 2. Integrate from 0 to 3. So we get 8/3 times 9/2 minus 0. 9 over 3 gives me a 3. So we'll get, let's see, just cancel that, get a 3, cancel that. 8 over 2, I get a 4, and cancel the 2. So I get 4 times 3. And my answer is 12. Okay, here we've got another triple integral. And we're integrating y squared, where d is the region between z equals x squared plus y squared and z equals 4. So this one, I've got sort of x, y, and z all tied together, so I can't sort of do that cylinder trick here. So I got to think about what these are. First thing, I'm going to look at z equals x squared plus y squared. When I see x squared plus y squared, I think cylindrical in this case, or polar, which is essentially the same thing. Whoops. Move down here. So what I'm going to do is that z equals x squared plus y squared. In polar, that's effectively, or cylindrical, this is effectively z equals r squared. And so if I graph that, what I'm going to get if I do sort of a z, I give it sort of as a zr plane, z equals r is this, and then sort of polar theta is going to rotate this around 0 to 2 pi, and so I'm going to get some kind of paraboloid like this. So I get a sort of bowl. It's like a cone, but it's curved in terms of parabola. And then I have z equals 4, so somewhere up here at 4, z equals 4 is going to be plane. That's going to cap that off. So I've got a picture of my region here. What that's going to look like in Mathematica. Better picture is this guy here. So this bottom thing is the paraboloid z equals r squared, or z equals x squared plus y squared. And then the top is that plane z equals 4, so the sort of blue-looking plane here on top. This circle is z equals 4. So that's what we're going to try and do. Now, to integrate that, what I'm going to do is I'm going to switch to cylindrical. So in cylindrical, let's see, y squared. Y is r sine theta. So I'll get r squared sine squared theta. My Jacobian, I pick up another r. So it's a poorly written theta there. And then what I'm going to do is I'm going to look at my sort of setup, my region to figure out the order. If I look at this, z goes sort of from this bottom function to this top function. So I'm going to let z be the inside bound. I'm going to do dz. And then dr, d theta, I just need those to sort of describe the shadow of this. If I sort of project down in z, well, that shadow is going to be this circle on top. If you sort of move this to the z equals 0 plane, or just sort of ignore the z. It's going to be this circle on top here. So I have to figure out what the radius of that circle is here. But z, the bottom function is r squared. Top function is z equals 4. And now that circle, well, that's when z equals 4, and it's also z equals x squared plus y squared. So that sort of disk on top is 4 equals x squared plus y squared. Well, that's a circle of radius 2. So r is going to go from 0 out to 2. And then theta, we're going all the way around, would be 0 to 2 pi. So this is your setup here. And then I'm going to integrate with respect to z first. So I get integral 0 to 2 pi, integral 0 to 2. R times r squared is r cubed. Sine squared theta. And then you get a z. It goes z from r squared to 4. Dr d theta. And then I go 0 to 2 pi, integral 0 to 2. Let's see, we get r cubed, sine squared theta. we're going to multiply this by 4 minus r squared, dr d theta. Okay, now I'm going to integrate this with respect to r. So what I'm going to get is an integral from 0 to 2 pi. I'm going to pull that sine squared theta outside of the integral. I have an integral 0 to 2. I can sort of distribute them the r cubed here. So I just like pulling, the sine squared theta has no r in it, so it's like a constant, so I can pull it outside the integral. I think it just looks nicer here, and I don't have to worry about like trying to integrate sine squared just yet. So I get 4r cubed minus r cubed times r squared is r to the 5th dr d theta. So now we want to do this inside integral. So we get an integral from 0 to 2 pi. We've still got this sine squared theta hanging around. And this is going to integrate to, let's see, r to the 4th. So r to the 4th over 4, the 4's cancel. Minus r to the 6th over 6. And that goes from r equals 0 to r equals 2. And then we'll have to integrate with respect to theta yet. And so we get an integral from 0 to 2 pi. Let's see. 2 to the 4th is 16. Well, I should have my sine squared theta first. And then I have 16 minus 2 to the 6th is, let's see, well, I'm going to cancel one of the 2's with the 6. So I get over 3, and then I'll have 2 to the 5th, which is 32 d theta. And this, let's say I could simplify this. 16 is going to be 48 thirds minus 32 thirds. It's going to give me 16 thirds. Integral 0 to 2 pi sine squared theta. Let's rewrite that. Sine squared theta d theta. So that's what I've got. And now I need to take this, I need to integrate sine squared theta. There's a trig identity that allows me to do that. Sort of a standard trick here. And that is that sine squared 2 theta is the same thing as 1 minus cosine 2 theta over 2. So this is just a trig identity, which maybe seemed weird as to why you'd want to know this when you did this, but it allows you to change sine squared theta into something you can integrate much more easily. And so I can pull out the 2, and I'm going to get then an 8 thirds, pull out the 2 in the denominator, which is really a 1/2. Integrate 0 to 2 pi. Well, let's just integrate these now. We'll be left with 1 minus cosine 2 theta. Integral of 1 is theta. Cosine 2 theta, so negative cosine 2 theta, would integrate to 1/2 sine 2 theta, or negative 1/2 sine 2 theta. And then we go from 0 to 2 pi on theta. So we get 8 thirds times, let's see, 2 pi. And then we get, let's see, sine of 4 pi is 0, so that doesn't show up. And then I plug in the 0, I get a 0, sine of 0 is 0. So I end up, when all is said and done, with 16 pi over 3. Okay, next question. Here we want to, whoops, too far, evaluate the triple integral of x, where our region we're integrating over is in the first octant between, okay, this sort of wrapped over, but it's x squared plus y squared plus z squared equals 1, and x squared plus y squared plus z squared equals 4. So this one, what I'm in the first octant, so that means that x is greater than or equal to 0, y is greater than or equal to 0, z is greater than or equal to 0. And I'm between x squared plus y squared plus z squared equals 1 and x squared plus y squared plus z squared equals 4. Those are spheres of radius 1 and 2. So what I'm thinking about here, let's see if I can draw this. So it'd be x, y, z. There's like a sphere, maybe of radius 1, something like this. And then there's this outer sphere of radius 2. That's going to go down here, down there. And you're sort of, I don't know, so between these two shapes here. But then I sort of want to draw out there. So you've got sort of a, I don't know, I think of it as sort of a boiled egg without the yellow sort of part in the middle here, but it's like a quarter of that. Picture of it. Better is right here. So here's your picture here. So you've got sort of a sphere on the outside. You've only got an eighth of the sphere here because you're in one of the quadrants and there's 8 quadrants. And this outside one is the sphere of radius 2, but then there's sort of this shell here. You've got this hole here where you have a sphere of radius 1. So this is the shape we're trying to integrate over here. Now this one, probably what you're going to want to do here, almost certainly, is do this in spherical. You've got two spheres. They're going to have nice spherical bounds. Other bounds are going to be kind of ugly. In principle, you could do things that way. It's just sort of would be hard. So I'm going to set this up in spherical. X in spherical is rho sine phi cosine theta. My Jacobian in spherical is rho squared sine phi. This particular integral I can do in sort of whatever order I want. Whoops. Let's do this. How about d rho d theta d phi? And then I just have to set up my bounds. So phi, let's start with phi. Phi starts at the positive z-axis here. Well, maybe let's look here. So positive z-axis is up here. Phi goes down until it gets to the xy plane. So it sort of starts up here and it sort of angles down. Well, the xy plane is phi equals pi over 2. So my phi range is going to start at 0 and then go down to pi over 2. If I went to pi, I'd pick up things with negative z. Theta, in the xy plane, we start at theta equals 0. And we're going to sort of sweep out until we get over here to the positive y-axis, which is going to be theta is pi over 2. So both theta and phi go from 0 to pi over 2. And then rho is going to go from sort of the inside sphere, which is radius 1, to the outside sphere, which is radius 2. So there's our setup. Now we just need to evaluate this. What we get, okay, so it's going to do rho first. We have rho squared times rho. That's a rho cubed. So it's going to give us a rho to the 4th over 4. And we have a sine squared phi cosine theta. And when we integrate our rhos, we get rho to the 4th over 4 from 1 to 2, d theta d phi. And what we get, let's see, we get 0 to 2, 0 to pi over 2, well, 0 to pi over 2 for both. Still have our sine squared phi cos theta. Let's see, 2 to the 4th is 16 over 4, minus 1 to the 4th is 1/4, d theta d phi. I left that as 16/4 because I knew I'd get a denominator for it. It's just simpler to subtract that way. So 16/4 minus 1/4, that's a 15/4. I'll bring that out in front. And then I want to integrate with respect to theta. So we get a sine squared phi, but then the antiderivative of cosine theta is sine theta. Theta goes from 0 to pi over 2, d phi. So we get 15/4 integral 0 to pi over 2. We have sine squared phi. Sine of pi over 2 is 1. Sine of 0 is 0. So that's just a 1. That 1 minus 0 effectively drops out as a factor. It's multiplied by 1. So we just have to integrate sine squared phi, which we did on the last question, or the same type of integral. The trick is, again, you replace sine squared phi with 1 minus cosine 2 phi over 2. That's a trig identity. And now you have things you can integrate. So you get 15/8 integral 0 to pi over 2, 1 minus cosine 2 phi. Ugly phi there. And then I integrate, so I get 15/8. And let's see. 1, the antiderivative of 1 is phi. Antiderivative of cosine 2 phi, negative cosine 2 phi is going to be negative sine 2 phi over 2. Integrate from 0 to pi over 2 with my phi's. So I get 15/8. Plugging in pi over 2 gives me a pi over 2. Sine of pi, or 2 times pi over 2 is sine of pi. That's 0. I plug in a 0, I get a 0. Sine of 0 is 0. So what I end up with is 15 pi over 16. One more. Last one here. So we want to find the volume of the region that lies inside both the sphere x squared plus y squared plus z squared equals 4 and the cylinder x squared plus y squared minus 2x equals 0. So what we've got is a sphere of radius 2 centered at the origin. This is a cylinder, but it's not quite the normal setup that we have. So let's try and rewrite this cylinder equation. I'm going to do x squared minus 2x plus y squared equals 0. And then I'm going to complete the square here. So I have to add a plus 1, then x squared minus 2x plus 1 is x minus 1 squared, but I have to add a 1 on the right as well. So what I end up with is x minus 1 squared plus y squared equals 1. So that is a cylinder. It's radius 1, but it's not centered at the origin. It's centered at x is 1, y is 0, z is 0. So if I draw this, maybe one of the nice ways to draw this is in the xy plane. Let's just do this in xy. This is a cylinder. Let's see, let's put this 1. There's 2. So it's really going to be a circle of radius 1 centered at 1, 0 here. And then z would be 0. X squared plus y squared plus z squared equals 4. If z is 0, I get a circle of radius 2. So this outer sort of sphere, I'm going to get sort of a big circle, something like this here. So what we've got here, you want to think about this red thing that's a sphere, and then I'm going to sort of chop through it with a cylinder being this blue thing. So I'm going to get some kind of shape, which I'm going to struggle to draw. What I think about in terms of setting this up is I'm really going to go from this circle of the cylinder, and there's going to be some bottom z and some top z that are sort of defined by the equation of this sphere. So to get a better picture of what's going on, let's look at Mathematica. And now I'm going to scroll down. Look here. So here's an idea. So the blue thing here, like this is backwards from the colors I used in the sort of notes there, or in the working through it, my own drawings. The blue thing is the sphere. The red is the cylinder. So you can kind of see here, you have this cylinder. There's sort of the picture we had before is you had this circle. It's sort of a little bit skewed, but the sort of sphere is this big circle, and then you had this sort of smaller circle inside, and that's a cylinder chopping down through the sphere. And you really want the region that's inside both of those. Well, that's going to be this sort of looking piece here. Sort of line this up. This top part is the sphere. Here, this side here is a cylinder, and then you get sort of a sphere on the bottom. Here you can kind of see that shape there as I go on. So that's sort of the sphere, the intersection of the sphere and the cylinder. So that's sort of visually what's going on. And again, my idea for setting up the bounds is I'm going to take this region. I know if I sort of rotate this over, I get that circle that sort of defines the cylinder that's going on. And then I can integrate z goes from the bottom to the top. So I'm really going to think of this sort of that way here. I'm probably going to end up doing this maybe in cylindrical. Okay, so let's set up our integral. So what I'm going to get now for my integral, I'm going to do a triple integral. Let's do this in cylindrical. We're finding volume, so we're integrating 1. But then our Jacobian in cylindrical is r. And I'm going to do this dz, dr, d theta. Okay, so now z, well, that's going to go from the bottom of the sphere to the top of the sphere. What's that sphere in cylindrical? Well, when I have x squared plus y squared plus z squared equals 4, x squared plus y squared is r squared plus z squared equals 4. So let's see, z squared is 4 minus r squared. So z will go from negative square root 4 minus r squared to positive square root 4 minus r squared. Those are my z bounds. And then my r and theta bounds just need to sort of describe this circle here. So I'm not quite sure what that is just looking at it, or maybe you're not. What you can do is use the equation x squared plus y squared minus 2x equals 0. So when we start with x squared plus y squared minus 2x equals 0, convert everything to cylindrical. X squared plus y squared is r squared. I'm an ugly r there. So r squared. 2x is minus 2r cos theta. That's 0. I can move the 2r cos theta to the other side. As long as r is not 0, which is going to be sort of an isolated point, so I don't really care, I can divide by r. And I get r equals 2 cos theta. So what we're going to have here is sort of this outer part, these r's, they're going to start at the origin. We'll draw about in this letter, but they're going to start here and go out to the circle. So we'll have sort of these radii that start here, go out to the circle. Start here, go out to the circle. Start here, go out to that circle. And I'm going to start at r equals 0. That's the origin. And out to the circle, which is apparently 2 cosine theta. Now theta, this one's a little bit trickier. So you got to think about, when am I at the origin here? Well, I'm at the origin when 2 cos theta equals 0. That is when cosine theta equals 0. So we get really r equals 0. Well, that's theta would be, say, negative pi over 2, or pi over 2, or 3 pi over 2, or 5 pi over 2, and so on here. So that would be when r is 0. So what we want to think about is when we're mapping this out, here we start maybe at r equals 0. Or we start somewhere. If we start at r equals 0, we could start at, say, negative pi over 2. Cosine, starting at negative pi over 2, cosine is going to be positive. So I'm going to start here, move around, and we go to pi over 2. We're still positive on this radius, and we'll end up there at pi over 2. So when we go from negative pi over 2 to pi over 2, we actually do one full circle. So note here, this theta bound is negative pi over 2 to pi over 2. You could also do just sort of any interval of length pi. So you could go 0 to pi. So if you did 0 to pi, you'd start out here. You'd go through, this would be at pi over 2. And then when you go from pi over 2 to pi, you have negative radius. So you're sort of over here in theta, but the radius is negative, puts you back here. And you'd get the circle once from 0 to pi. So a common mistake here would be to go to 0 to 2 pi. And then you'd be sort of going over the circle twice. And you'll end up with twice the volume you should. Okay. Now we have our integral, we just need to evaluate this. I'm a little worried about the square roots, but this r looks like it's going to sort of save the day there. So I get an integral from negative pi over 2 to pi over 2. Integral from 0 to 2 cos theta. When I integrate r, really, 1 times r is r with respect to z, I get rz. And I'm going to go from negative square root 4 minus r squared to positive square root 4 minus r squared. dr d theta. And then when I integrate that, I still have my negative pi over 2 to pi over 2, my 0 to 2 cos theta. So I get r times, when I plug in square root, 4 minus r squared, just square root 4 minus r squared, and then minus a negative, so I'll get plus r times square root 4 minus r squared. And then dr d theta. These two terms are the same, so I end up with an integral from negative pi over 2 to pi over 2. Integral from 0 to 2 cos theta. I have 2r square root 4 minus r squared. dr d theta. And now I can integrate this with a u equals 4 minus r squared. du would be negative 2r dr. I've got the 2r out there already. I just need the negative. So I'm going to integral from negative pi over 2 to pi over 2. Pick up an extra negative that I'm missing. And let's see, I do square root of u is u to the integral of square root of u is u to the integral of u to the 1/2. That's u to the 3/2 over 3/2, or 2/3 u to the 3/2. So I get a 2/3 4 minus r squared to the 3/2. And we go from 0 to 2 cosine theta. d theta. Worries me a little bit here. And what we get, let's see when we plug in, we get a negative 2/3. Whoops, we get an integral from negative pi over 2 to pi over 2. Now we get a negative 2/3. When you plug in 2 cosine theta, you're going to get 4 minus 4 cosine squared theta to the 3/2. And then when I plug in a 0, I have to remember to do that. I'll get a plus 2/3. This will just give me a 4 to the 3/2. So d theta. So what I get, let's see, an integral from negative pi over 2 to pi over 2. Let's see, 4 minus 4 cosine squared theta. That's actually 4 sine squared theta. So I get negative 2/3 4 sine squared theta. But that's raised to the 3/2. And then plus 2/3. Let's see, 4 to the 3/2. Square root of 4 is 2, and then cubed is times 8. d theta. And so we get, let's actually pull out the 2/3 here. We should have done that a while ago. Negative pi over 2 to pi over 2. Let's see, 4 sine squared theta. Square root is going to be 2 sine theta. I've got a little bit of an issue here. It should really be 2 sine absolute value of theta here, because sines can be negative here. So one solution, we're finding the volume here. I want sort of the absolute value. Could have, instead of doing negative pi over 2 to pi over 2, what I could do is just integrate this from 0 to pi over 2, and then I get a double that. So essentially what that's doing is I'm finding the volume of the top half of this, but then it's symmetrical, so I should find both. Or sorry, not the top half of this. I'm doing theta from 0 to pi over 2. So I'm essentially finding the volume if I split this sort of along a line here, and I'm finding the top half. 0 to pi over 2 would give me sort of the, well, now the top half, I guess, versus the bottom half. So I'm splitting sort of the long way here, and I'm cutting that in two. In my picture up here of this circle, I'm really finding the top half here. So I'm really finding the volume that's above this sort of green upper semicircle here. And then when you sort of could double that to get the bottom due to symmetry. And I'm just doing that to not have to deal with absolute values here. So when I do that, what I end up getting is, let's see, 4 sine squared theta. I take a square root, give me 2 sine theta. Again, I don't need to worry about the absolute value if I'm only going from 0 to pi over 2. And then when I cube 2 sine theta, I'm going to get 8 sine cubed theta. And I pick up the negative from the negative 2/3. And then I have a plus 8 here. D theta. And so let's say I get 4/3. I can factor out an 8. That'll give me a 32/3. Integral 0 to pi over 2. I'm going to write the 1 that's left after I factor out the 8 minus the sine cubed theta. And now what I'm worried about most is integrating that sine cubed theta. So to do that, what I'm going to do is use some trig identities. So I get a 1 minus, I'm going to write sine cubed theta as sine theta times sine squared theta, d theta. And then what I can do is take the sine squared theta and write that as 1 minus cosine squared theta, d theta. And let's see, what I get is integral 0 to pi over 2. Let's see, we distribute these out. We get a 1 minus sine theta plus sine theta cosine squared theta, d theta. And then the trick is sine theta cosine squared theta. I'm going to let u be cosine theta there, and then du is negative sine theta, d theta. And so what I end up with is 32/3 times antiderivative of 1 is theta. Sine theta gives me a, well, negative sine theta gives me a plus cosine theta. Sine theta cosine squared theta would give me a cosine cubed theta over 3. Essentially, u squared goes to u cubed over 3, but I pick up a negative. So I get a minus cosine cubed theta over 3. And all this is evaluated as theta goes from 0 to pi over 2. And all we've got left is to evaluate. So we get 32 over 3. So you do the pi over 2, we get pi over 2 from theta. Cosine of pi over 2 is 0, so the next two terms are 0. When we plug in the 0, we get a 0 for theta. Cosine of 0 is 1, so we get a minus 1. And then we get a minus negative is plus 1/3. Again, cosine of 0 is 1. So we can clean this up a little bit. We get 13/3 times pi over 2 minus 2/3. So we could use a 6 as a common denominator inside the brackets. And we get a, let's see, 3 pi minus 4 over 6. And then we could cancel a 2 here. And we end up with 16/9. Whoops. Said that right, wrote it wrong. 16/9 times 3 pi minus 4. Let's write that nicer, though. 3 pi minus 4. And there is our answer.